pictures, they would have these large camera like aerial pictures and manually adjust the rays of the cameras before in film. Yeah, it's sort of old school map building. That's where the name comes from, and it's been used in computer vision.
Okay, because there's also the term model is also used in topology. I don't know that
in the museum.
That's right, map tangent, but
Yeah,
I was kind of wondering whether it had something to do with that.
I think it's one of those pretty nifty and obsolete.
I wasn't doing yesterday, but they talk about how converting the spaces and just finding things like the definition of it. It's really cool. Anyways, but is Steve on things?
What's that?
That's scary. Okay. Can't hear it. Jason, can you start the camera?
So I can't see much of anything. Just Ben.
Oh, Ben, did you like share your slides on Zoom? Or I can just turn this.
Yeah, that's fine too. Perfect.
Okay, if it's fine then. Okay, I just turned the camera so it's in Slam Core. Three 436 714.
I see.
Beautiful.
What is so quiet? Steve Fine.
I tried.
Are you sure it's coming out of this? Can you try for your computer for me too? Do you mind speaking again?
Sure, no problem.
There you go. Perfect. Okay.
Everything working?
So technical difficulties all figured out. Let's get started. So I'm going to be talking about modeling relative factor graph and some scan registration. So this is the outline of what I'll be talking about today. The first maybe third or so is going to be going through relative formulation of the factor graph, and then provide a specific example using reprojection errors and landmark models. Yeah. Tied yesterday. And then the rest of the lecture is going to be specific examples of point set registration. So what it is, and some popular and some a couple of algorithms that I found interesting because I can include them if I want. It's my presentation. So relative graph representation. The main difference between this and the absolute formulation is that in the absolute formulation, state vector is it's 3D poses of all of the robot positions along its trajectory, as well as the positions of the landmarks. And they're all given in a single unified coordinate frame. However, you can also, of course, specify them relative to each other. So in that case, this is kind of a graphical representation of what it looks like. So P in Sidney's relative bundle formulation, P is a set of 6 element vectors, each representing SE3 twist. L is the landmarks. And the landmarks is kind of interesting because, as I said, not in an absolute frame, you have to specify them in a relative frame. But you can pick whichever frame you like that sees it. So what Sidney does those use the first state that saw that landmark is the state that the landmark is stored. So L is a set of 3 element vectors, just Euclidean kind of position that nature with respect to some state. And T are your actual estimation parameters. So the way this works is that the relative transform from some state to another state, it's P in composed with T. So the solid lines in the graph, those are lines having their own T vector. And the idea of it is that you have your total transform being the concatenation of the two, is what this thing at the bottom is. But the thing with the caret, so that's the transform from J to alpha, that's kind of like your previous estimated transform, and this T subscript J would be like your estimation increment that you're adding to it. So the solid lines all have that incremental kind of T subscript J, which means that, and so for the features, that means that there's only one solid line with that associated with the measurement, right? Because only the state that the landmark is specified relative to means incremental. Okay, great. So
So the T's are always between P's, between the positions.
So the T's are always between positions. So along the trajectory, you have n positions, you have n minus 1 T's, but you also have T's coming from the landmarks themselves. So the first time you see a landmark, you have kind of the estimated transform of it, and you also have this T, which is an incremental thing you can optimize over. So
You
you
still have confused, so what is the capital T versus with the small t and the transforms?
yeah, so
The capital T is
that's just the number of transform. So yeah, as a warning, lots of these algorithms that we'll be talking about are taken from different sources. So the notation will be a little bit changing here or there. Just kind of stop me if it's unclear. Yeah. So there are n minus 1 T's coming from the states and also however many landmarks. Guess not?
So L11 refers to, because there's an L11 and an L12, right?
Yes.
And so the second, is that J and L the same J as from T?
So L11, it's saying landmark 1 specified in P1.
Ah,
Yeah. And then landmark 2, as seen from 1, is like L12.
that's landmark 2 seen from 1, I see. Okay.
Yeah. And it holds for all the big pieces. And the measurements are also kind of specified in similar manner. So measurement between some state and the landmark 111. So state 1 measured to landmark 1 in that
Frame.
same frame.
Interesting.
So that's the graph. Now, as an example, how you would get the Jacobians for this, this is reprojection error seen from yesterday, probably using different notation. So the objective function is the one on the bottom. That's reprojection error in a camera projected space, Z, IJK, which is measurement from state I to landmark J as seen in frame K. Subtracting the measurement model for that landmark given X, which is the vector of all the states. So H being the measurement model, it's specified as the projective function from the landmark to the camera. So the T inverse J I, that's, you take the inverse of it, it's the transform from frame J to I, J being the frame of the landmark, and I being the state you're measuring that landmark from. So it's got a couple of components. So G is taking the 3D position in homogeneous coordinates and transforming it to the vehicle frame in Euclidean coordinates. M is mapping from the vehicle coordinate to the sensor frame coordinate, still in Euclidean space, just because they may not be like coincident. think of our car, for example, we have our base, we have our center of the rear axle would be our vehicle frame, but of course each camera has its own frame. So that's what the M does. It also takes care of any like conventions or any rotations caused by convention. So like what's the standard for cameras? Some axis is down, something like that. For cameras, the axes are flipped compared to like yeah. So that's what that is. And then K, that's the projective function we saw yesterday. So you should all be familiar with that. So we have our we have the Jacobian. We take a Jacobian of this. We can take it with respect to the landmark position and also with respect to the transforms along those little T's, T and C. I think I might have spoke earlier. T and C's are from every point between the path and also loop over the surface. Whereas the landmark states are only 3 element vectors. So when you take these derivatives, you do the chain rule, and you get 6 things you have to evaluate.
What is capital R?
Where is it? Oh, R. So that is the uncertainty on the. So that would be some covariance. Take the inverse of it, you get the information form. Now you have Mahalanobis. So looking at that first transform, right, from J to I, you can see that if I is the frame you observe the feature in, and J is the frame the feature is specified in, do the transform, you have to go all the way along the kinematic chain. And here, there's a couple of those incremental transforms that are part of it, but only DC is shown just for keeping it not cluttered. But this shows how these TCs make their way into the Jacobian through this kinematic chain. Back to these functions. So I'm sure you all remember the second presentation course, which was calculus and 3D orientations. That's where this Jacobian is coming from. I'm not going to go into it because you can always go back and view. But it's the Jacobian of the transform using an element on SE3. So that box with a subscript X, that's the skew symmetric mapper. So that's you have some 3 vector, right? Take it to the skew symmetric matrix. So that's our first Jacobian. Our next Jacobian is taking that Jacobian with respect to the projection function. So you have some points, M1 to 3, multiplied by the projective function matrix, and then you scale it by the last element. Because you scale it by the last element, it's not a linear transformation, so you have to go through, use quotient rule, and you arrive at a final form. The remaining Jacobians are pretty simple because they're just linear mappings. You just take the constant. You put it all together, and you get your final Jacobians, which will go into, there'll be elements of your measurement matrix. This is that measurement matrix. So the sparsity pattern of this matrix, it's very similar to the absolute formulation for vector graphs. The only big difference is that you get these extra, sometimes you get these extra bands, right? These bands are coming from those kinematic chains because now you've introduced dependencies on like measurements in your landmarks of all the states along the kinematic chain from the state you're measuring from to the state your landmark is specified in, which kind of makes sense. But that said, say you're moving along.
Sorry, what was the kinematic?
The kinematic chain is the chain between the state you're taking the measurement of the landmark and the first state you saw with the landmark in. So because that transform depends on every state between, you get those extra terms in your Oh yeah, so you get these extra terms of theory, but actually, if you think about the absolute formulation and observing features, you tend to kind of observe a feature, see the same feature in the next state, and so on and so on. So they tend to be kind of contiguous. If all the landmarks are seen by contiguous states, then you get the exact same pattern and there's no change in sparsity. So why would you want to use this relative formulation? Well, the main advantage of this relative formulation is that you have it's in a very natural form to do incremental updates. I'll talk about that just in a couple slides. The downside of this is that with your relative formulation, it's pretty expensive to convert it back into a unified framework. So if your application requires a globally consistent map, and it requires you to have up-to-date globally consistent maps, this is probably not the best, but there are plenty of applications where you'll really need a locally kind of Euclidean space to do your object detection or planning or whatever in. So it's an acceptable representation. So this partial update. So think about if you're adding a state to this relative formulation, and then you put in your measurement utopia, and you've gone through, you're solving it, not in your iterations, you have some kind of factorization, and you're starting to back substitute to find the rest of your states, right? So as you do this, the first back substitution you can make is your newest state, and then the states that are attached to it, kind of along the factor graph. And so instead of going all the way along the graph, you can just stop, or you could stop if the update is less than a certain amount, because it's not going to affect the subsequent states that much. And so that's what this is showing here. In kind of the graph version of it, you're doing a breadth first search, starting from your most recent state until you find a state that isn't changing that much in that case. What's interesting, you could do this in the absolute formulation, but what's different about the relative formulation is that even if you have a loop closure, you still have a limited number of states that you update. And that's because in the relative formulation, even though the whole loop might have some absolute error, relative along, like state to state along your loop, it's not going to be that high. So when you do the update, only the endpoints of the loop actually change that much. And so even if the loop is super long, you don't have to update the stuff when it is out. You can just stick to the stuff that's close by. Whereas in an absolute coordinate system, as soon as you've you've translated one end of the loop, the whole loop is moving, right? So you have to do a much more expensive update. So any questions on the relative formulation before I go on? Because after this, I'm going to go into scan registration.
Did you get it, all the information on how to do the relative?
Can you speak up?
Oh, I was going to say, did you get the information on how to do the relative? Can't remember. From one paper.
Sorry?
Did you get that information from one paper? Reading one paper? Or
Yeah, most.
most?
Is there a notation?
No, it's just like it sounds very familiar from the pre-integration paper where they talk about doing the updates in the relative manner rather than the global manner.
Yeah, it's kind of similar to ISAM. Actually. And this paper came out 2 years before ISAM, so maybe it was an inspiration. But yeah, it's the same kind of thing. You have to factor, just do the back substitution.
Yeah, because in terms of visual odometry, you don't care about the global. You really care about. You don't really care about how you. When you do the updates, you probably want to do relative rather than globally.
Well, visual odometry isn't SLAM, right?
No.
So it doesn't have.
No.
Okay. Let's move on to scan registration. So, scan registration, you have two sets of points. Oh, it's also called point set registration. So you have two sets of points, and you want to find some way to align them to minimize some error, right? So there's all sorts of kind of different ways you can formulate your cost function. The dimensionality of the set, rigid, non-rigid, right? Point level. I'm not sure what's meant by point level, but I'll tell you during the homework session. So rigid, non-rigid. So if you have, say you have like two static point clouds taken with a laser scanner, some distance apart. And the laser scanner has no motion, right? So there's no motion distortion or anything, and there's no kind of stretching between the points. A rigid transformation is one that preserves distance between points. So because there's no stretching between the point clouds, it's okay to use this transformation to simplify the problem. Non-rigid transform doesn't do this, right? So it allows for that the points may have moved, stretched in more places than other places. Like think about you take an MRI scan of a lung, for example. The guy's breathing, right? So it's different pictures are the points on each, the feature points are going to be stretched differently across the image. So you want to use a non-rigid algorithm to find the correspondence between each point. But it's more expensive because there's more feature stuff than else. So I'm going to start with everybody's favorite rigid transformation, ICP. This one's from 1992, I think. It's very simple. It operates directly on points. The idea is take a reference, you have a reference scan, and you get another scan of your environment. For every point in your environment, you try to find the closest point in the reference scan, and then transform to minimize the distance between all those points. So this cost function is pretty much just showing that. The epsilon there, that's just the transform parameters. T of epsilon is the transform given those parameters, transforming the point in your scene scan to the reference scan. P epsilon of j is the corresponding point. W of j is a weighting factor. So in the original ICP, it's either 0 or 1 based on how far apart your corresponding points are. The idea being, if you know your scans are only displaced by X number of meters, if something is 10x, if the correspondence is 10x away, then it's unlikely to be correct, so you don't have to, you shouldn't do it.
So you got a,
Yeah.
I got a question. What if they're on the same number of points? Guaranteed the same number of points.
So that's the thing. So this is an image of ICP in AdWord. The lines are the correspondences. They're the final correspondences. So at each iteration, where it solves the optimal transform, it does the whole thing over again, finding the closest points. So that's why in this image, these lines are connecting the closest points in their current displacement, but they're the final ones. What happens when one downsides to ICP is that because it operates directly on a number of points, it's greatly affected by point density. So if there's a really dense number of points, then some sparsity right here, you're going to tend to get more correspondences to the dense points, even though it might not be quite right. So if you have like a really sparse scan matching to a dense scan, you'll probably have, or the other way, you have a really dense scan matching to a sparse scan, you'll probably have a lot of points getting corresponded to the same point in the reference scan, which I think is what you were referring to there.
Yeah, kind of. Yeah, I mean, basically, you're allowing that. So that was kind of answer the question I didn't ask.
Yeah.
But it was a good question, which is you're allowing.
Yeah, you can have things be the same, correspond to the same point. There is actually a variant of it called iterative dual correspondences, where you find correspondence the other way, and then you only keep the ones that are each other's correspondence. But it's just more expensive. Although, I guess only 2 times more expensive.
But you therefore don't share your mapping thing, which may be completely unrelated.
You're mapping things that maybe
You're mapping points that you're mapping multiple points to the same point.
yes.
And maybe for that reason, maybe these points Well, it's clear that one of those,
Yeah.
some of them are not.
Some of them are not right? Well, it's because it's designed to be very simple, right? So the heuristic used to match point is closest to me. That's it. Right? It's not,
And
it's
if
not
one, let's say one of the two is denser, you just don't know, you have no points in that hash, whatever, and then any of them could be corresponding.
Yeah.
If you just go back one step, so what was epsilon again?
What was which?
I just would like to understand the
Yeah.
elements of
What
the
you're asking?
equation. So what is epsilon?
So that is the parameters for your transform. So it could be a determinant, it could be a twist vector that will pitch you out.
And Pj with the epsilon, what's that?
That would be point in the reference.
Okay, and then you're finding the transform. Okay, on the Pj is the measurement.
Yeah.
And what you're trying to register.
Yeah.
Function.
Okay, so as we just talked about, ICP has a few shortcomings, but it's spawned a whole class of related algorithms that try to
So I still don't understand, because epsilon will be the parameters the parameters of the transform. Why would it be parameters why would it be P? What has why would you superscript P?
Yeah, that's kind of strange. This is taken from Abreen's thesis, so I'll ask him and get back to you guys. So these problems with ICP.
Sorry, I didn't quite get the question.
So the question was if go back. The question was if epsilon is parameterized in the transform, why is Pj superscript of epsilon? Presumably is the point in the reference scan, and it wouldn't depend on epsilon.
Oh, yeah, okay, that's interesting.
Anyway, so I see some problems. So people have been trying to solve.
It looks like it's an R on this slide, is that right?
Yeah, the notations. Well, I'll explain what R is in a bit.
Okay, sorry, carry on.
So generalized ICP was an algorithm that tries to deal with kind of this resolution issue. So making the assumption that points in a scan are locally planar, they're not just these random clouds of points, then you can use that structure to try to match in a kind of more intelligent way. So in generalized ICP, what you're doing is around each point in a local neighborhood, you're doing principal component analysis, and the minimum eigenvector, you take that to correspond with the normal of the local plane of the planar surface. Then what you do is you represent the covariance of that point as kind of this pancake shape. So that's this, some of that. The top left element is some element less than 0, and the rest of the elements along the diagonal are 1. So if you visualize this in 3 dimensions, let's say, you can, that epsilon across the ellipse would be quite short, and then 1 would be like this disc shape. And so once you have this S, I, R, and S subscript I, superscript R, that's your rotation of that covariance matrix into common frame, into the base frame of the reference scan. Because you're finding the covariance matrix in the local frame at that point, so you have to rotate it given the normal, which is the N I of R, to the common reference scan. So you do the same thing with your scene scan, like with this normal, right? And then you can throw it into a Alanovus cost function, which is this thing at the bottom. Alpha I is the point-to-point distance, and S are the rotated covariance matrix. The reason why there's some epsilons on this one is because those are your optimization numbers. And alpha of I would also depend. Oh yeah, there it is over there. Alpha I also depends on the translation.
When you said local neighborhood, does the PCA Is that like a heuristic that's just defined on the input, that like the size of a local
The size of a
neighborhood, or is-
local neighborhood is a heuristic. Usually it's defined not as like a distance, but the number of nearest neighbors.
right?
Yeah.
So that's a because what might be a surface planar would change in your scan, right? It's not going to be fixed, so you have to just kind of pick one that would best kind of
Yeah.
generalize. You can't optimize.
I mean, I'm sure it's been extended all sorts of ways. Like this covariance matrix, there's no reason you couldn't have epsilon change depending
Sure.
on the CA output.
Yeah.
But
Because that's what I was wondering, if the PCA actually figured out what the best size of the surface planar would be at a given area. But
no, not so much.
Okay.
As far as I remember, you take the eigenvalue decomposition of covariance within a neighborhood. It's not much.
But the neighborhoods here would like in an IFL would be some kind of
Integer.
cubes or
No, it'd be integer number of points.
but you would take those points. I mean, you have to take them from a neighborhood. Right?
A neighborhood around the point.
Also, it's more like a sphere.
Yeah. It'd be a sphere. Usually you use like approximate nearest neighbors, so approximate sphere. Is there anything that's not clear about the notation before I go further? Okay, we'll keep going. So these are kind of I couldn't find a picture somehow of these covariance surfaces. So this is my quick and dirty version. You can imagine the ellipses of those pancakes. The short dimension is lined up with the normal of the open plane area. And you can, even in this kind of simple example, you can see it doesn't do so well around the areas that aren't planar. Right? Like consider the bottom point here. It's not too useful. So if you have to say like a forested area, this isn't going to be great. So another pretty popular matching algorithm.
The pancake idea is not exactly clear to me.
The what?
The pancake idea is not exactly clear to me.
So it's the probability distribution shape. It's the shape of the probability distribution. It's always flat, right? But it's quite long. So yeah.
And that's for the this one is the probability distribution of the normal vector. Surface normal vector. See how that's the pancake.
Well, it wouldn't be shaped exactly like a pancake, right? But it would be it'd be flat and elongated, circular, because you're saying of the covariance is diagonal, right? But you have one very small element, and the rest are ones. So if you were to draw, say, the one standard deviation confidence of that covariance, you'd have it in one dimension be quite thin, but the other dimensions are going to be quite elongated. Anyway, don't get too hung up on the pancake. It's just kind of explanatory. So NDT is another popular standardization algorithm. And it's kind of taken a more probabilistic approach to matching. So the idea is instead of working directly on the points, you convert the points to probability distributions and match against those. The probability distribution question is in the normal distribution. So the way that would work is you take you subdivide your scan into regions. And within each region, take the mean and sample covariance in order to fit a Gaussian. And then once you fit the Gaussian to it, you can match based on the probability that the point in your scene scan came from that distribution. So notation in this case, thing on the top, that's the probability, that's the likelihood function of a Gaussian. The mean and covariance are coming from your sample mean, sample covariance within some region, what you're trying to match. And then your objective function is the sum of all those after you're transforming each point by your optimization parameters. B is the difference from point B, or the point to the mean of distribution, and you can sum this up over all. So there's two ways you can do this. You can convert the reference scan to distribution and do point to distribution matching, or you can convert the close to distribution and do distribution to distribution matching. The thing on the left of the blue line, that's the point to distribution version. The thing on the right is the distribution to distribution, which is why it's a little bit more complicated. The thing on the top, that's the difference between Euclidean difference between the means after it goes to the transform. And this is another element of this distance. So you're adding the covariance after rotating.
So is this a distribution of points outside?
So this is what it looked like. So in the original NET version, you're breaking up the scan based on grid size, and then doing a sample mean, sample covariance within each grid to produce a probability distribution. So what that looks like is here. This is a visualization of the probability within each grid. So for grids that only contain a line, you get this really thin Gaussian, right? But then for stuff where there's kind of stuff all over the place, it's a little more blurred. And you're matching like this. As you look at this, you might notice that between some of the boundaries, that it's quite discontinuous. That's true. So there's a few extensions that you can do. You can try to match not only against the nearest distribution, but the nearest, say, 9, gives you a smoother probability surface. But actually, the way that you subdivide the original scan is completely independent from the matching. So one of the things you can do is cluster into K clusters and do a coarse-defined refinement. So that's what this is showing. So you're going from 3 to 9 clusters. So you do the thing on the left, you get kind of these spread out Gaussians, match against those, move down, segment fewer Gaussians, match against those until you reach your stopping point, whatever that may be. This helps with avoiding local minimums and makes it a bit more robust to initial timing error. And then, I think that's all I want to say about NET, because it could be its own topic. And then the last rigid algorithm I want to talk about is correlated scan matching, just because it's a little bit more recent. And this one, it also takes a probabilistic approach, similar to NET, where you're trying to maximize the likelihood of your points. But it uses a completely discrete representation of probability distribution. So rather than converting to Gaussian, subdividing it, something like that, it actually works directly on the reference scan. So each point is given this kind of isotropic covariance, and it's broken up into discrete grids and summed up the probabilities. So this would be like a lookup table on the left, this raster version, where each light point is due to one or more nearby points that have added probability to it. What this allows you to do, having this discrete one, is kind of a branch and bound approach. So you can add or course define refinement, let's say. So, which is actually this is what cartographer uses. So what you can do is inflate this initial raster at different amounts to give you different resolutions, right? So that would be, say, this thing on the right, where within each box, you're taking the highest probability and assigning that probability throughout the box, where you're inflating inflating the highest probability within a point to cover the whole box. And so that means if you match against the coarse one, that the final probability you get with your best match is guaranteed to be an upper bound on the fine graph. Any questions? Because that's
Kind of lost me. So first of all, X1 is a scan point in the scan, or is it more like some kind of you know, I guess root or element of the object? So yeah.
okay. So this is saying the probability of state x subscript I. This is the baseline for it. So
Oh, you talk about the state, like well, for example.
so you're trying to maximize the likelihood of the measurements,
Yes.
right? So you have the up on the right using Bayes' rule, it's proportional. Up on the right, you have the probability of the measurement given the state, which would be your transformation parameters, right? And M, which is your environment model. And M is that raster that I just showed. It's multiplied by
What is U1 with Z?
I'm getting to that. On the right would be the motion model. So this is xi minus 1, your previous state, plus u, which might be some input or process model. So if you match against a coarse one like this, the final score you get is guaranteed to be an upper bound on any of the any of the finer resolution distributions. So what you can do with this is, in the 2D case, it extends to 3D, but let's stick to 2D for now. In the 2D case, if you search along an angular window with these coarse graphs, you can do a branching bound approach. So you do, for each angular increment, you do your coarse matching and you find the optimal match score for each angular displacement. From there, you go into your best one, and you go down until you go down to the next level and do the same thing, except you don't have to search along the angular direction. So you just have to slide these linear displacements around. And because each increment of this linear displacement can be done parallel, it's sped up through G, right? Once you've done that, on your next step down, you can compare your best score to the level up, coarse score, to the best possible upper bound on the other orientations. And if the best possible bound on those upper orientations, any of them that are higher than your score that you found in your lower bound, you need to go for that one to make sure there's not a better match obtained with them. I'll draw a tree of this in the homework section. So one of the things I haven't really talked about yet is scan uncertainty. So when you're incorporating these scans in a factor graph, you usually want to have some notion of uncertainty. Otherwise, what doesn't really tell you anything. In this case, because you sampled the cost function in so many places, you can get a covariance from that. So it's quite natural. Don't dwell too much on these equations because it's specific to the algorithm. The idea is more that you have a probability distribution. You've sampled it in a number of places, so you can approximate covariance of the match based on the scores you got in those places. It is overestimating the covariance just because you haven't sampled the space exhaustively, but it usually is pretty good compared to ICT covariance, which I'll talk about shortly. Here is a couple of covariances calculated using the scan matching method. You'll notice in the hallway case, it does accurately capture the fact you're not constrained along the hallway. These are confidence ellipses. So uncertainty in general, you're kind of, each algorithm will have its own approach you can use. This guy, Sensi, he was able to find a we applied general method to ICP, which incorporates some sensor covariance to kind of give a better approximation to the real covariance. But the problem in general with trying to find covariances with local methods is that they tend to be overconfident. So it's like ICP as an example. If you go back to this hallway case, and you're looking at the Jacobian approximation of Hessian, which is telling you how fast the cost function is changing, it's usually used to try to arrive at some estimate of covariance, because it's the covariance of the cost function, right? But the problem is that it's not taking into account the changing correspondences as you move along the hallway. So even though you might get a very similar score if you move some distance down the hallway and do ICP again, because it's not redoing correspondences, you'll discover there's an increase in cost holding the correspondences constant. If that makes sense, because the points you're matching against are moving apart. GICP would be less affected by this because you're moving in the stretched direction on those covariance abilities on the surface. So Gaussian mixture models. So mixture models are just some number of distributions. Gaussian mixture models is when those models are Gaussian. So just some quick background because we're going to have to go through. So coherent point drift. This is an example of a I'll say semi-popular non-rigid registration method. And the idea with this is that we try to find the smoothest velocity field to transform points to their correspondences. So what's meant by smooth velocity field is helpfully shown by this graphic. So for the choice of correspondences with B, it's fairly smooth, less smooth with C, even worse with D. So that's fine, but how do you put that into the cost function? Well, here, y and x are your point sets. And so you first consider y as a Gaussian mixture model. And each point in y is a centroid or mean in that mixture model. And then you're trying to transform all those points according to the mapping in the top right, which is the velocity function, given the plus the initial position. You're trying to maximize the probability of x, your measured points, by maximizing the likelihood against this Gaussian mixture model made from the points in y. So the likelihood function, it's the sum of each, because it's a mixture model, right? It's the likelihood of each point in x with each Gaussian mixture model. You sum those up, and you use a isotropic covariance. This is describing one element in the mixture model, so it has a mean at some point in y, and it has a isotropic covariance. So
Sorry, what was the y0?
y which?
Y0.
Y0. That's your initial position points in y. So you're transforming them in order to maximize this likelihood function. Right.
The idea is that you transform from y0 to y that would match x.
Yep. Yep. So this is the probability for one point. This is the probability for all your points, or log probability. Now this extra term on the right, this is actually the term that's imposing the smoothness constraint. So it's regularizing, it's penalizing high frequency noise or high frequency energy in your velocity field. And I'll talk more about this next slide. Oh, and gamma is just a scale parameter. So it's this, like, if you want a better match to the data, or do you want a smoother velocity field? So it's actually kind of similar to Levenberg marker, where you have that extra line to break across. You're right. Looking at it upside down. So you want some function to penalize high frequency noise, which is the metric in this printing that's used in coherent point drift to penalize non-smooth velocity fields, right? Because if it's a non-smooth velocity field, it'll have lots of high frequency components. So what you can do is you have the velocity field, take the Fourier transform of it, and sum up the power in the high frequency regions. So G, this is some sort of low pass filter that tends to zero as S goes to infinity, right? So easy. So you can imagine it's as you get higher and higher frequency, it's weighting the higher frequency components of V higher, and so penalizing them more. Make sense? Okay. So you plug this in to your objective function for this form. And keep going. So I invite you to look at the appendix in the paper on coherent point drift, but skipping that, the function that is minimizes the energy of the previous objective function is this thing. So this is a Gaussian kernel. It's like a bunch of Gaussian kernels weighted together. A Gaussian kernel, you can think of it as you give it some vector, take the squared L2 distance, and that is, and put it into zero mean Gaussian probability function, Gaussian kernel. So you have your velocity function, plug that in, and do some simplification, and you get it work with this. So that's fine. So what you're actually optimizing here are W, which are the weights in your Gaussian kernel, as well. Oh, actually, that's it. Yeah, just W. But if you look at this thing and you're trying to optimize it, it's kind of nasty. So what's used is expectation. So you factor out this P matrix. So P is a matrix of all the posterior probabilities from the previous iteration. So it's the probability of some point in the scan with its corresponding distribution of the Gaussian mixture model divided by the chances that it's corresponding to any of the other distributions of the Gaussian mixture model. So yeah, that sums to one. This term on the right, this is actually inserted into the denominator of each element in P, and it represents a prior probability that it might be the case that the point you're trying to match doesn't actually correspond to any points you understand. So D is the dimensionality of your point of your Gaussian, which I guess is 3. We live in the real world. And then A, you adjust this to weight the prior probability compared to the chances that it matches to one of the distributions of the mixture model. So in this way, correspondences are found probabilistically, and you can weight the chance that it might just be noise. It doesn't correspond to anything. So looking at Q, that's not the cost function, that's the upper bound of the cost function. This is more appendix stuff. So if you minimize the upper bound on the cost, you're also minimizing the actual objective function. So you can do it in steps. So taking the root of the upper bound with respect to the weights, you can solve for the weights at 0, right? Take the derivative, set it to 0. That's what that equation copies. And you can just follow these steps through, find your optimal velocity field. It does, so there's 3 free parameters in coherent point drift. Lambda is controlling trade-off between smoothness of the velocity field, and fitting data. Beta is the distance or covariant or variance of the Gaussian kernels. So this controls how strongly neighboring points affect each other. And then sigma is the standard deviation used for the isotropic covariance of the Gaussians in the mixture model. So this deterministic annealing, all this is doing is taking the original sigma and shrinking it. The idea being that the larger sigma is, the more spread out these Gaussians will be, so they'll affect more points. And so you do it with kind of a wide sigma to get a coarse alignment, shrink sigma down, and you just keep going until you're happy. And this is what it looks like. So quite good results, but I mean, it's expensive if you didn't already guess. So I don't want to do any other non-rigid algorithms because they're pretty complicated. So this one, so these algorithms, right, they're all kind of designed for, I don't want to say ideal point clouds, but definitely not ones that look like our Velodynes, right? So in our Velodyne, there's motion distortion, of course, right? Extreme roll and shutter. Scan takes some of the time to complete, but you're driving a car, so this is one pole, but it shows two. It's highly anisotropic, so you get really good resolution along the laser scan. You get really good resolution along the swept dimension, but each laser detector pair is located something like 3 degrees apart. So you get nice lines one way, but then big gaps the other. Other practical considerations, so usually you want this to run in real time, kind of localized, and you need some estimate of covariance. That's why, another reason why ICG maybe isn't the best. It's difficult to get that. So this is a specialized kind of scan matching example. So it uses it's almost designed for these LiDAR scanners that have really good one-way resolution. So, and it uses motion distortion actually to solve for velocity. So the way it works is you have an IU or VO, right? Providing an estimate of the non-constant velocity during the LiDAR scan. Then using that non-constant velocity, you can transform each point, depending on the time it was measured, to a common reference point. Once you've done that, you can extract features that are designed for these highly anisotropic sensors and match those features from one scan to the next. And the kind of neat thing about this is you don't necessarily need to take into account IMU bias, because IMU bias is very low frequency kind of drift effect, and that will actually get corrected when you do the scan-to-scan item. So these are the features that Bowen was using. So it's kind of pick up edges and planes in the environment. This is a kind of curvature score function. So you're going along one of these lines and calculating the score. So S, that is the number of points you're including in your kind of local curvature calculation. X, L subscript AI, that is the location, or that is the distance to your point you want to calculate the curvature for. And then you're summing up the difference between that point and all of its neighbors. So if it were a perfectly flat line, that sum would go to 0, right? Because it's symmetric. And then if it's a point, we'll get a much higher score. So you do this along each line of your LiDAR. You pick the high points, the high curvature to be edge points. You pick the low points to be linear points. Then you go back to your previous scan, and you can match against these points. So on the left here, this is the example of trying to find correspondences for an edge point. You try to find an edge point, the closest edge point, and also the edge point in the neighboring line scan. Then you can draw a line between those 2 points and do a point-to-line distance metric, put in the optimization. Similar story for the plane, except you have to find 3 points to the plane.
So here in the LiDAR feature, like, even it's an edge based on depth, so you can just, in a white room, then you can just pick up borders or edges.
Yeah, because you have depth information. I mean, you can use any visual feature will work in LiDAR, but the problem is practically, you usually don't have the kind of resolution.
No. Let's go.
So this is this cost functions I was talking about earlier. Yeah, it's just distance from a point to a line and distance from a point to a plane. Don't worry too much about all the subscripts because you can look that stuff up. All right. Any questions about scan methods? Which one should we use? That's a good question. I mean, it depends. For our car, I think both would be good. And maybe combine some aggregated point clouds with correlated matching would also be good. You can do, you can make it 2.5. One thing I didn't talk about actually was maps, right? You know, always matching scan to scan. So if you keep like a map made from several scans together, you can match against that. And what's been done is a Gaussian mixture model map. So you can think of this as a occupancy grid, except that within each cell, you're not storing the properly being occupied, you're storing a mixture model of the height.
How severe is the?
How what?
I was going to say, how severe is the? Remember how you said that there was, from a single light pole, you could detect it twice because of motion.
Or its apparent position changes. Right? Yeah. But it's not that you really detect it twice, because it'll detect it at each point. It's the apparent positions.
Oh, right. So
how severe?
Yeah.
It depends how fast you're going and what the rate of your LiDAR is.
Is there information at like highway speeds?
I mean, we can do a quick calculation. Like highway speed is what, 35 meters per second, let's say. So multiply that by 0.1 seconds. So 3.5 meters at highway speed. Yeah.
have you checked out Velo?
I kind of wonder how much of for example, the scanning for probable objects we're talking about.
Which
Non-rigid.
non-rigid. Okay.
Can see how you could use that for tracking.
Yeah, that's another thing I was thinking about, right? But the thing is, it's so expensive. So I think you have to find some way to trim your point clouds down if you want to apply method like that. But yeah, it'd be pretty good for initialization, right? Because it just picks up the velocity field signal that. Actually, it's been used for tracking the shrinkage of like an iceberg.
It's a different type of tracking.
Have you tried Velo?
There's no, it's not open source, is it?
Oh, I don't know. I just heard about it on the Kitty data set.
Oh yeah, it's ranked up there.
Yeah.
Yeah. I mean, it's Loam and its kind of extensions they're built to be this hierarchical structured approach, right? So if you have the LiDAR odometry part, the visual odometry in front.
Yeah.
Okay.
Nicely done. Great summary. Okay, so next week, what do we have for the course?
So